Two stars, dead and dense, spiral toward each other in absolute silence, each one no wider than a city, yet heavier than the sun. These are neutron stars, collapsed cores of once massive suns, now locked in a fatal dance. And when they collide, the universe listens. In 2017, Earth felt the tremor of such an event from 130 million light years away. But what if it happened closer? Not in another galaxy, but right here, within our own. In this video, we'll explore what would happen if a neutron star collision occurred just 1,000 light years from Earth. The gravitational shockwaves, the radiation burst, the potential damage to satellites, power grids, even the ozone layer. This isn't science fiction, it's astrophysics. And it's something we're watching for right now. So if you're fascinated by the edge of space science, cosmic danger, and how the universe reveals its secrets, make sure to like this video, subscribe to the channel, and join me on this journey into the heart of stellar destruction. Because when neutron stars collide, they don't just shake the heavens, they rewrite the rules of physics. Two stars, dead and cold, spiral toward each other in silence. Each is no wider than a city, yet heavier than our sun. They are neutron stars, the remnants of supernova, crushed so tightly that a teaspoon of their matter weighs billions of tons. They orbit closer with each second. Gravity pulls them inward, dragging space and time along for the ride. Their motion generates ripples, gravitational waves that stretch across the universe. This process takes millions of years. But the final seconds pass in a flash. The stars circle hundreds of times per second, then crash. The impact unleashes forces unmatched by anything else in the cosmos. One such event was detected in 2017. It was called GW170817, and it happened 130 million light years away. Even from that distance, Earth-based detectors like LIGO and Virgo felt its tremor in spacetime. But what if it happened much closer? Not in another galaxy, but within our own. What if a neutron star collision took place just 1,000 light years from Earth? The consequences would be immediate and global. Because neutron star collisions are not just gravitational. They release powerful electromagnetic radiation, gamma rays, neutrinos, and relativistic ejecta. First comes the gravitational wave burst. Our detectors would light up with the most intense signal ever recorded. It would confirm the event's proximity, direction, and mass with razor-sharp precision. Next, telescopes across Earth and in orbit would detect a flash. This is the short gamma-ray burst, a pulse of high-energy radiation lasting just seconds. Despite its brevity, it carries as much energy as the sun will emit in its entire life. If the collision occurred within 1,000 light years, the gamma-ray burst could threaten Earth's atmosphere. It could deplete the ozone layer, exposing the surface to ultraviolet solar radiation. This effect would be short-lived, but severe, potentially altering climate and biology. Satellites in orbit would suffer immediate damage. Radiation hardening might protect some, but many systems would fail outright. GPS, weather forecasting, and communication systems would face widespread disruption. Airplanes flying at high altitudes would receive radiation doses well above safety limits. Flights over polar routes would be especially vulnerable, where Earth's magnetic field offers less shielding. In extreme cases, rerouting might be necessary for weeks, but this is just the beginning. The real impact arrives seconds later, in the form of relativistic jets. These jets, traveling near the speed of light, are made of plasma, particles, and magnetic fields. If Earth lies in the direct path of a jet, the consequences escalate. Charged particles would interact with our magnetosphere, triggering massive geomagnetic storms. Auroras would stretch to the equator, and power grids could be overloaded. Transformer stations would trip offline. Satellites would be knocked out of alignment or permanently damaged. In worst-case scenarios, parts of Earth could experience long-term blackouts. Meanwhile, neutrino detectors would log a sudden spike. These nearly massless particles pass through matter as if it weren't there. But their abundance during the collision would offer insights into the exact nature of the neutron stars. Cores. What remains after the collision depends on total mass. If the merged object is under a certain threshold, it becomes a massive neutron star, temporarily stable. If it exceeds that limit, gravity wins, and a black hole is born. Around this new object forms a kilonova, a blast of heavy elements hurled into space. Gold, platinum, uranium, these atoms are forged in the heat and pressure of the explosion. In fact, much of the precious metal on Earth likely came from a neutron star collision billions of years ago. But when the event is nearby, those same elements become a radioactive cloud. Ejecta moving at relativistic speeds could eventually pass through the solar system. Most of it would miss, but even tiny amounts could affect satellite shielding and sensor calibration. The light from the kilonova would reach Earth as well. It would appear in the sky as a new star, slowly fading over days. For a while it would outshine all other objects except the moon. Astronomers would watch as the spectrum changed. Blue at first, shifting red as the cloud expands and cools. Each spectral line a clue to the elements being created in real time. Radio telescopes would track the afterglow. As the shockwave plows into surrounding interstellar gas, it produces synchrotron radiation. This tells us about the energy of the explosion and the density of the space around it. Theoretical physicists would analyze every frame, every frequency. They'd refine models of neutron star interiors, regions so dense that atomic structure collapses. Some speculate that exotic forms of matter exist there. Quark-gluon plasma, hyperons, or strange matter. If the collision produces gravitational waves with non-standard polarization, it might hint at new physics, possibly even deviations from general relativity at extreme energies. This is where observation becomes a probe of fundamental theory. But even with all its destructive force, a neutron star collision at 1,000 light-years is not an extinction event. It's close, but just far enough to spare Earth from its worst outcomes. Still, it would be the most energetic, disruptive, and scientifically valuable cosmic event in recorded history. At 100 light-years, the gamma-ray burst becomes catastrophic. Its energy, no longer diffused by distance, strikes Earth's upper atmosphere with full intensity. Within seconds, it obliterates a significant portion of the ozone layer. The ozone layer shields Earth from solar ultraviolet radiation. Without it, UVB and UVC rays penetrate to the surface in lethal doses. Plant cells, plankton, and animal tissues suffer DNA damage almost immediately. Within days, photosynthesis begins to decline. Phytoplankton, the base of the marine food, chain die in vast numbers. Oceans lose their capacity to absorb carbon dioxide, accelerating climate change. Land-based crops begin to fail. Chloroplasts in plant leaves degrade from UV exposure. Global agriculture enters a critical state in weeks. UV radiation also causes widespread human health effects. Skin burns, immune system suppression, and ocular cataracts rise sharply. Outdoor exposure becomes hazardous in broad daylight. Air travel is grounded across entire continents. High-altitude radiation from secondary cosmic rays renders flight routes unsafe. Satellites are shut down or damaged beyond repair. Global navigation systems fail. Military communication is disrupted. Weather prediction models lose accuracy due to damaged satellite instruments. Power grids come under stress. Induced currents from geomagnetic storms damage transformers and substations. Blackouts sweep across major cities, from North America to Europe. Space agencies struggle to respond. Lunar and Martian missions lose contact as deep space antennas suffer cascading signal noise. Emergency protocols are enacted to safeguard remaining satellite infrastructure. The neutrino burst floods detectors for hours. These signals help reconstruct the internal collapse in exquisite detail. But they also confirm that the event is unprecedented. In human history. As the relativistic jets fade, the kilonova follows. Its light is blinding, clearly visible during daylight. For days, the sky is wrong, unnatural, impossibly bright. Astronomers scramble to model the ejecta. Spectral lines shift hourly. Heavy elements like europium, actinides, and lanthanides are synthesized in the aftermath, but fallout becomes a new concern. Radioactive particles from the merger travel outward in a slow-moving spherical cloud. Depending on solar wind conditions, fragments could reach Earth within years. Radiation sensors across the globe go on alert. Increased atmospheric ionization is recorded at upper altitudes. Though small in quantity, this radiation adds to the environmental stress load. Biosphere stability declines. Amphibians, already sensitive to UV radiation, face regional extinctions. Migratory birds lose navigation cues due to geomagnetic field disturbances. Deep-sea species remain largely safe. Ocean depth protects against radiation and UV exposure. But surface ecosystems enter a prolonged state of collapse. Governments initiate climate geoengineering proposals. Aerosol injection, high-altitude reflectors, and artificial ozone regeneration are debated. But time is limited and resources are strained. In parallel, physicists begin analyzing what the event reveals. How stiff was the neutron star equation of state? Did the waveform contain evidence of quark matter or chiral symmetry breaking? Supercomputers are tasked with reverse engineering the gravitational wave signal. They aim to reconstruct the final milliseconds before collapse. This helps refine the conditions for black hole formation from neutron star remnants. Particle physicists explore whether Strangelet's hypothetical clumps of strange quark matter could have been produced. If so, they might have survived the journey and interacted with Earth's matter. This would open a new chapter in beyond standard model physics. Meanwhile, new missions are planned. Satellites hardened against gamma radiation. Lunar-based telescopes. To escape Earth's damaged atmosphere, the public's perception of the universe shifts. No longer abstract or distant, cosmic events now feel local. Space becomes not just fascinating but dangerous. At 100 light-years, a neutron star collision would change civilization. It would not destroy Earth, but it would challenge its biosphere, atmosphere, and infrastructure to the edge. Recovery would take decades, and the skies would remember. The remnant would persist for centuries, a glowing reminder of stellar violence. Its radio waves and expanding shock front would remain visible long after the event itself. At 10 light-years, the energy impact becomes direct. Not just radiation, but sheer momentum and particle flux overwhelm Earth's natural shields. This isn't disaster recovery, it's global system failure. The gamma-ray burst would sterilize exposed surfaces. Its energy, measured in ergs per square centimeter, crosses the lethal threshold. All upper atmosphere molecules are ionized instantly. The ozone layer is destroyed in minutes. Nitrogen oxides form in abundance, triggering chemical chains that block natural regeneration. Earth's sky becomes transparent to UVC, the most biologically destructive radiation. Skin cancer rates would skyrocket within weeks if populations survive that long. Plant growth halts, even under artificial light. Global food systems collapse not from economics, but from biology itself. The relativistic ejecta from the merger arrives soon after. Jets of plasma, magnetically confined, deliver ionizing radiation to the magnetosphere. Auroras ignite at the equator, an atmospheric signature of planetary trauma. Earth's magnetic field struggles to deflect the incoming wave. But the jet is orders of magnitude stronger than any solar flare. Satellites are vaporized, and the International Space Station is lost instantly. Terrestrial electronics short-circuit en masse. Geomagnetically induced currents overload power lines and data centers. All global communications are reduced to local systems, many of them permanently offline. Nuclear power facilities enter emergency shutdown. But without electronic controls, cooling systems fail. Radiation leaks become unavoidable in many locations. Civilization collapses in stages. First from communication loss, then infrastructure, then biological systems. Governments are powerless in the face of a sky that is turned lethal. And then comes the shock front. Even traveling at a fraction of light speed, debris from the collision carries mass and momentum. When it reaches the solar system, it disrupts the heliosphere itself. Solar wind is overtaken. Comet orbits change subtly. Outer planet atmospheres show signs of chemical disturbance. Earth is not struck directly by stellar debris. It doesn't have to be. Even the edges of a kilonova cloud at this range deliver megatons of radiation to the upper atmosphere. Long term, this accelerates climate destabilization far beyond current anthropogenic models. The biosphere shrinks to refugia caves, ocean depths, underground shelters. Surface species begin a wave of extinction, starting with large mammals and migratory birds. The Cretaceous-Paleogene extinction was milder by comparison. No photosynthesis means no oxygen renewal. Carbon dioxide accumulates without check. Marine life dies not from temperature, but from acidification and suffocation. Only species with radiation resistance survive. Tardigrades, deep-sea microbes, fungal colonies. Humanity survives only where deep shielding exists. Underground bunkers, deep mines, polar subsurfaces. Neutrino detectors will have long since overloaded. But their data tells the final story. From waveform asymmetry, we deduce that a hypermassive neutron star formed. Briefly then, collapsed into a black hole. The gravitational wave signature is burned into digital archives. It becomes the final alert received by deep space telescopes. After that, silence. No warning system on Earth could respond fast enough. Even if the collision were detected, the gamma burst would arrive within minutes. At 10 light years, there is no time to prepare. This is the boundary of survivability. Closer than 10 light years, and the energy becomes too intense for the atmosphere to protect us. Within 1 light year, even planetary orbit could destabilize from relativistic mass effects. Fortunately, no known binary neutron star systems exist within that range. Our closest candidate, PSRJ 04374715, is a millisecond pulsar 500 light-years away. For now we are safe, but neutron star collisions still matter. They build the heavy elements in our bones, our electronics, and our DNA. They are both threat and origin. They are the death of stars, and the reason planets like Earth even exist. And in every direction, across every galaxy, they still collide.